In our previous session, we had done types of flows. Now let us start off with the momentum, Euler's, Bernoull'Is, and energy equation. The continuity equation says nothing about the pressure in the flow. We know just from intuition that pressure is also an important flow variable. Difference in pressure from one point to another in a flow creates forces that act on the fluid element and causes them to move. Hence, there must be some relationship between pressure and velocity, and it will be discussed in this session. We first consider the fundamental law of physics, the Newton's second law, which states force is equals to mass into acceleration. That is, F is equals to ma. To apply this principle to a flowing gas, consider an infinitesimally small fluid element moving along a streamline with velocity v. At some given instant, the element is located at P. The element is moving in the direction x, where x-axis is oriented parallel to the streamline at point P. The y and z axes are mutually perpendicular to x. The fluid element is very small, that is infinitesimally small. Physically, the force is a combination of three phenomena. Pressure acting in a normal direction on all six phases of element, gravity acting on the mass inside the element, and frictional shear acting tangentially on all six phases of the element, explained in relationship with change in pressure, density, and velocity as Euler's equation and Bernoull'Is equation. For time being, we will ignore the presence of frictional forces. Moreover, the gravity force is generally a small contribution to the total force. Therefore, we will assume that the only source of a force on a fluid element is pressure. To calculate the force, let us assume the dimension of the fluid element to be dx, dy, and dz as shown in the figure. Consider the left and right faces which are perpendicular to the x-axis. The pressure on the left face is P. The area of the left face is dy dz. Hence, the force on the left face will be P of dy dz. This force is in the positive x direction. Now, the pressure varies from point to point in the flow. Hence, there is some change in the pressure per unit length, which is derived by dp by dx. Thus, if we move from the left face to a distance of dx along the x-axis, the change in pressure is dp by dx into dx. The pressure on the right face is P plus dp by dx into dx. The area of the right face is also dy by dz. Hence, the force on the right face is P plus dp by dx into dy and dz. This force acts on a negative x direction. The net force in the x direction, F, is a sum of these two. So F is equals to negative of dp by dx into dx, dy and dz. Because of the convenience of choosing the x-axis in the flow direction, the pressure on the faces parallel to the streamlines do not affect the motion of the element along the streamline. The mass of the fluid element is the density ρ multiplied by the volume dx, dy, dz, so we get m is equals to ρ into dx, dy and dz. Also, the acceleration a of the fluid element is by definition of acceleration rate of change of velocity. So a is equals to dv by dx into v. Euler's equation relates to the rate of change of momentum. It is important to keep in mind the assumption utilized in obtaining we neglected friction and gravitational force. Hence, when we substitute F is equals to m into a, we get dp is equals to minus rho v dv. Now let us move on to the Bernoull'Is equation. If the air flowing past the top surface of an aircraft wing is moving faster than the air flowing past the bottom surface, then Bernoull'Is principle implies that the pressure on the surface of a wing will be lower above than below. This pressure difference results in an upward lifting force. At low speed, the flow is incompressible and the density is constant. The surface of airfoil is streamlined, velocity varies and is used to compute the change in pressure. The pressure along the entire airfoil gives the total aerodynamic net force on airfoil, which is then resolved into lift and drag. So P plus rho v square by 2 is equals to constant along a streamline. Now consider 2 points 1 and 2 which are far away from each other in a flow but on this same streamline. To relate P1 and V1 at point 1 and P2 and V2 at the other point 2, we must integrate between 1 and 2. This integration depends on whether the flow is compressible or incompressible. Euler's equation holds good for both. For compressible flow, rho is a variable, and for incompressible flow, rho is constant. When we consider incompressible flow, we get a constant rho. So we get P plus rho v square by 2. Let us consider a case of incompressible flow. Let point 1, point 2 be located on the given streamline. Such cases we get P1 plus half rho V1 square is equals to P2 plus half rho V2 square. For compressible flow, Euler's equation must be used. That is, dP is equals to minus rho V square. 1. Hence the equation P1 plus half rho V1 square plus P2 plus half rho V2 square and P plus rho V square by 2, which is for constant streamline, are called Bernoull'Is equation. Bernoull'Is equation is one of the most fundamental equations in fluid mechanics. The equation we use for compressible and incompressible flow holds only for inviscid, that is frictionless incompressible flow. The equations of compressible and incompressible flow where rho is constant and variable relate properties between different points along the streamline. For compressible flow, the equation dP is equals to minus rho v dV must be used with rho treated as a variable. Bernoull'Is equation must not be used for compressible flow. Remember that the equation dP is equals to minus rho v dV and P1 plus half rho V1 square is equals to P2 plus half rho V2 square, and the equation P plus rho V square by 2 are all dependent on F is equals to ma for a fluid flow. They are essentially Newton's second law applied to fluid dynamics. Energy equation. Energy equation has a physical principle which states that energy can be neither created nor destroyed. It can only change from one form to another. Compressible flow, high-speed flow, and massive change in energy go hand in hand. High velocity indicates high temperature and low velocity indicates low temperature. Energy equation relates to the temperature and velocity at two different points along the streamline, which can be given by C subscript P T plus half V square is equal to constant, where Cp indicates the specific heat at constant pressure, temperature indicates T, and V is equals to velocity. This equation relates the temperature and velocity at two different points along the streamline. Again, if all the streamlines are of a uniform flow far upstream, then this equation holds for any 2 points in the flow, not necessarily on the same streamline. Moreover, this equation is just as powerful and necessary for analysis of a compressible flow. I hope you would have understood the Euler's equation, Bernoull'Is equation, momentum equation, and energy equation. Let us move on to drag in the next session. Thank you.